All right, now we're going to talk about conservation of energy, and believe me, there's more to come on this. Okay, so here it is. Law of conservation of energy. The total energy, E cis, equals mechanical plus thermal. So the total energy of an isolated system is constant. The kinetic potential and thermal energy within a system can be transformed into each other, but their sum cannot change. By the way, what's an isolated system? It just means that there's no interaction with the environment, between the environment and the system. That's what it means, isolated, right? No interactions between the environment and the system. Furthermore, the mechanical energy, K plus U, is conserved if this system is isolated and non-dissipative, right? Mechanical energy is conserved, no friction, okay? So that's it. So make sure you understand that. It's super, super crucial. Oh, golly. It's not so bad. So here, we're going to actually use this a lot. You're going to like it, I hope. Problem-solving strategy, energy conservation problems. Model, just like before, you always model, right? Define the system so there are no external forces or so that any external forces do no work on the system. You'll see how we do that. If there's friction, bring both surfaces into the system. Model objects as particles and springs is ideal. Okay. Visualize, draw a before and after pictorial representation. Now, Randy Knight loves these energy bar charts, right? So he says, draw the energy bar chart. I don't bother, but whatever. A free body diagram may be needed to visualize. Okay, here's the important thing. If the system is isolated and non-dissipative, that means no dissipative forces, no friction, then mechanical energy is conserved. Bingo! Well, we already used that a bunch of times, right? Where K is the total kinetic energy of all moving objects and U is the total potential energy, right? Could be gravitational, spring, you know. However, if there's friction, you know, right? If there's friction, then you can't use this, right? Because mechanical energy is not conserved. If there's friction, you got to use this. Big deal. You just add this, right? And that's not too hard to calculate. It's not a big deal. Where W dis equals F dotted with delta S, which is minus FK delta S. Check that your result has correct units. I don't care about sig figs. Make sure it's reasonable. Make sure you answer the question. That's kind of important, right? So let's see how you actually use this crazy thing. All right. A 200-gram block on a rough surface with mu K equals 0.8 is pushed against a spring with spring constant 500 newtons per meter, compressing the spring 2 centimeters. If the block is released, what's the speed? All right. Now, this doesn't sound like a physics problem. I don't, you know, a physics textbook problem. I don't know what it is, right? I mean, you got the friction, you got the spring. I mean, good golly. So, let's do it. Okay. What is the system? It's always a good idea to ask that. So what's the system? Well, you know, we got the spring attached to the wall, right? So we got the wall, the spring. Okay, what else? The block. No kidding, right? A block. Let's see. We need a table, right, or whatever it is, the surface, you know. So let's call it a table, because we need that for friction, right? We need that for friction. And what else? Earth, because of gravity. So the astronomers say that you should use uppercase E for Earth, so whatever, you know. All right. So here we go, right? Now, let's see. We have friction. So which equation are we going to use? We have to use this one, right? We have to use that one. No problem. Just write it down. Just write it down, you know. So let's write it down. So K initial plus U initial equals K final plus U final. Okay. All right. Now, what's not really nice about writing it like this? We're just going to evaluate every single term. That's all we're going to do. And you can see that's pretty simple. Okay, so let's see. We're pushing it against a spring, right? So it's not moving because it's being held against a spring, right? So kinetic energy initial is 0. Right? 0. Now, how many potential energies are there? There are 2. There's gravity and there's spring, right? So there's 2. Okay, well look at it. It's a horizontal spring. Agree? Better be. Yeah, it is. All right? So the initial gravitational energy is the same as the final gravitational potential energy. So we can just ignore it, right? Just ignore it. But just, it's there, Maybe I should just write it. I'll just say this. UG initial equals UG final. So we can ignore it, right? So ignore. Therefore, ignore it. Because it's going to be the same on both sides of the equation. So just, who cares? Goodbye, All right, so we get rid of that. Let me do it like this. So K initial equals 0. Okay, what's U spring initial? Well, just 1/2 K delta S squared, right? What's delta? Okay, all right. Okay, I did that. All right, then we do this. So what's K final? That's what we want to know, right? That's what we want to know. 1/2 mv squared. That's what we want to know. And what's U final? Okay, I already said that we don't care about the gravity. Okay, now it says the block is released. So that means that the spring is no longer compressed or stretched or anything, right? So the potential energy of the spring is 0. Okay? Oh, sorry. U spring final. Let's be nice. U spring, that means U spring final, right? U spring initial. I'm being lazy. Now, what's W dis? Well, we know what W dis is. We've done it a million times, right? That's W dis, right? W dis. So, and then, and what's Fk? It's mu K N. And what's N? Mg, okay? So I know we're kind of skipping steps, but that's all right. Okay, so W dis is minus Fk mu K Mg. All right? Yeah. Okay. All right, you ready? So now we just plug and chug. It's wonderful. So 0, okay, so that's 0. That's 0. Okay. 1/2 K delta S squared equals K final, 1/2 mv squared, or V final, I guess, whatever. That's 0. And minus is a plus. So plus, I can't believe I did that. Yeah, sorry. UK, MG, delta. So we have UK, MG, delta X. Right? Okay, everybody all right with this? Okay, so what do we want to get? We want to get the speed. So we just want to solve for V. Okay, so so we want to get this to this side. So we have, let's multiply everything by 2. Just get really stupid fractions. You don't have to, but that's what I do. Okay, we want to solve for V. So let's let's subtract that. So we have K delta S squared minus 2 mu K mg delta X is equal to mv final squared. Okay? Yeah. So then we divide by the m, take the square root. And we're done. Okay? Now, what's delta S? It's how much the spring is compressed. What's this delta S over here? Same thing, right? Same thing. So I could have just called it delta x initially, but I didn't. Okay, all right, so there. Okay, so you just plug and chug and you get the right answer. Ta-da! So look that's not so bad, right? I mean, that's the beauty of these things. I mean, look, we have friction, we have all this horrible, complicated stuff. But if you just write it like that, and then just evaluate every single term, you get the answer. It's not so bad. So study that, make sure you understand it, because that's kind of a typical problem, you know, typical problem. And again, it's, you know, you see the friction and you say, oh man, I can't use mechanical energy conservation. It's all right. We know how to calculate this. Right? We saw that last chapter and we saw it here. So it's always nice, right? Now, of course, if it's on a slant, you know, then you have to calculate the normal to get the FK, but it's all right. We've done that many times in the past. Okay, so there's that famous equation. Okay, let's do another one. So why don't you read that while I'm erasing? So, have you ever watched a TV show and there's a car that skids to a stop and let's say did something wrong, and so the police officer measures the skid marks, how long they are, and then the police officer determines whether or not the driver was speeding. Well, how do they do that? Well, that's what we're going to learn right now, okay? All right, so in screeching to a halt, a car leaves skid marks 65 meters long. The coefficient of kinetic friction between the tires and road is 0.71. How fast was the car going before the driver applied the brakes? Okay, so look, we have friction, so we can't use mechanical energy conservation, but we can certainly use that longer equation, right? So that's what we'll do. Okay, what's the system? Car, road, earth. What else is there, right? Okay, so we have friction, so we have to write down our favorite equation. Well, it's not our favorite equation, but K initial plus U initial equals K final minus plus U final minus W dis. That's our favorite equation when you have friction, right? Okay, now just like before, all you do is you evaluate each term, you know? Okay, so K initial, right, that's how fast the car was going before the driver applied the brakes. So that's just, you know, 1/2 mv squared. Or m and, yeah, put the initial there, okay? What's U initial? Well, we don't have any spring. All we have is gravity. And the car was on the road. We're going to call the road y equals 0. So we're just going to say U initial is 0. Goodbye, right? Okay. Now, what's K final? Well, I mean, at the end of the skid, the car is stopped, so K final is 0. What's U final? Well, the car is still on the road, right? Didn't jump and didn't do anything crazy, so that's 0. So we just have W dis, right? Okay, so, and we already know what that is, right? Because we've already seen it 50 million times. But okay, so W dis is Fk dotted with delta x. Let's just do it. Why not? W dis is Fk dotted with delta x. So that means it's minus Fk delta x, right? Because the angle between the friction and the displacement is 180. Cos 180 is minus 1. Okay, and Fk is mu k n, and then n is minus mu k mg delta x. So you should be able to do that in your sleep by now. I hope, right? Okay, so there you go. All right, so now we have minus this. So it's minus and minus is a plus. So mu k mg delta x. Nice. So what do you notice? Divide by the m, right? Then we multiply by 2, square root, and there you go. All right. So the initial speed, square root 2 mu kg delta x. So the delta x is the length of the skid mark. So that's why the police officer has to measure the length of the skid mark. You know? Okay, now notice a couple of things. It did not depend on mass, right? I mean, wouldn't that be horrible if the police officer had to somehow figure out the mass of the car, you know? So doesn't have to do that. Just measure the skid. That's all. But wait a second. How about the mu k? How does a police officer know what the mu k is? I don't know, to tell you the truth, but they probably measured like the tread depth of the tire. They probably have some kind of a, some kind of an app that gives them a guess. And then they, if the road was wet or had sand on it or something. I mean, let me put it this way. If you were a lawyer, an attorney, whatever, and you had a client who was charged for speeding, this guy, all right, and you're defending this person, and the officer measured delta x, but you don't want your client to be found guilty, what are you going to argue? The only thing you can really argue about is the mu k, right? You can say that the police officer used the wrong value of mu k, because what else is there? You can't argue about anything else, But anyway, that's pretty cool, right? So to me, that sounded like a pretty complicated problem at first, but if you just use this formula and figure out each term, it's not so bad, right? Not so bad. By the way, we could have used kinematics and forces. We also could have used that equation we used a long time ago, well, last chapter, right? We could have used that too. So there's many ways of solving this problem, but I don't know. I think this is cool. I think that's the best way. All right, so there you go. Okay, let's quit.